Hello everyone. Today we are um, going to see how to apply the influence line in a design problem. So we have here a beam structure with two internal hinge, and the beam has its own self weight of 0.5 kilonewton meter. And the question is, we wanted to get the maximum positive moment at D. So we need to find the influence line for moment at D. And once we find the influence line of the moment at D, where should we place the live load of 5 kilonewton meter, which is a uniformly distributed load in the beam such that we get the maximum positive bending moment at D. So that is the first part. And the second part is, if there is, in addition to the 5 kilonewton per meter live load, if we have a concentrated load of 15 kilonewton, where should you place them such that we have the maximum positive bending moment at D? So when you see this type of questions, first you have to ask where the what point, um, what is the function that is asking for. So we have here bending moment and at which point D. So, and what do we need to get? A maximum positive bending moment. So that means we need to calculate the bending moment at D, or we need to draw the bending moment at D. So in that case, to draw the bending moment, the influence line for the bending moment at D, we are going to use a Mueller-Brush law principle. What it says that you can introduce a internal hinge at D, because you have to release the restraint, because right now the joint D is a rigid, so we have to release the restraint um, of the joint D by introducing a hinge, because hinge can rotate can rotate easily. So which means that it can rotate, which means the moment equal to 0. So we have released the restraint or the constraint at D, and we apply a positive moment. This is the sign convention to apply positive moment in uh, Mueller-Brush law principle. And then once we have that, we are going to see how the beam will deflect. So in this case, we are going to draw the deflected shape of the beam once the beam has been applied this positive moment. And so you can see that this beam BC will have to rotate counterclockwise, because we're applying a moment, or we're applying a rotation of counterclockwise, and then the beam DE will rotate clockwise. And because this B is internal hinge, we say that internal hinge can move up or down and can rotate. So, and now we have the beam AB will rotate in that direction, and then for FG will also rotate in a similar manner to connect the joint. Okay, so so now let's see the criteria of Mueller principle. Mueller principle says that the criteria, once you apply a rotation for finding the bending moment, you apply a rotation. It should be a straight line. So we say that all of them are straight line. That means our criteria is satisfied. Why straight line? Because for determinate structure, the influence line must be straight line. And now second is, check for, uh, if we move any support. We did not move this support, we did not move this support, we did not move this support, we did not move the other support also. So we do not move any of the support, which means that uh, we we meet the criteria. And then third is, check for if we have damage or break or bend the beam. We didn't bend anywhere except here and B, but the reason we are able to bend the joint B is because it is an internal hinge, and we already said that internal hinge can move up or down and can rotate. And we did not bend anywhere here. Here we can bend because that's where we release the constraint, and we apply Mueller principle. So this one is exceptional. And then, and here also we did not bend. Here we again bend is because it is an internal hinge. And then here we also rotate is because the joint G and joint A are roller support, and we know that rollers or pin and roller support can rotate infinitely. So we don't have to, we did not uh, violate any of the criteria. So since we meet all the criteria, so that will this will be your influence line. So now the question is, how do you find the ordinate of this line? So the ordinate of this line, if this is a, the distance from C, then this is B. This ordinate is AB divided A plus B should be equal to 2.5. And if you don't remember the formula, what you can do is you can think this is theta 1 and this is theta 2. And we know that this whole thing will be theta is equal to 1. So we know that theta 1 plus theta 2 summation of two internal angle should be equal to external angle, and this is 1 radian because we apply a rotation of 1 radian or unit radian. And for theta 1 we have h, if this is the distance h, and h is equal to 5 plus h is equal to by 5, that will be theta 2. The reason we use theta 1 is equal h by 5 is because theta 1 um, is very small, and because it is very small, we assume that we can consider that theta 1 is close to tan theta 1 is close to theta 1. So in that case, that's why I said theta 1 is equal to h by 5, because if we take tan theta 1 as is h by 5 and must be equal to 1, so you'll find that h is equal to 2.5. So that's the ordinate of your influence line at D. And then the ordinate at B, we have to use the similar triangle for this angle, this two triangle. And for that, we will have, if this is your h1, then for that case you'll see h1 for a triangle CB, that will be h1 divided by 4 must be equal to 2.5 divided by 5. And from here you'll see that h1 is equal to 2, so this value is 2. And then this also is this is a symmetrical beam, so the distance is the same for F and B, so this also we can consider as 2. So now we can draw the full influence line. So this is so that will be influence line. This is A, this is B, this is C, this is D, this is E, this is F, and this is G, and the ordinate is 2, 2.5, and 2. And for this particular cases, because self weight of the beam is given, and self weight of the beam we cannot it will be across, so the self weight for this particular problem will be across the whole beam, because that's the self weight of the beam. We cannot ignore it, or we cannot uh, place it according to our desire, so the whole beam is the self weight of the beam. So in that case, so because we are interested to find the maximum positive moment at D, so we have to consider first the moment at D due to its own self weight. And we have learned that for a uniformly distributed load, it will be W, which is your uniform distributed load, and area of your influence line, where W is placed. So in this case, the W is placed all over the length. So that means we have to consider both of the all the area. So we have negative area here, positive area here, and negative area here. So if we put all the equation, you should get 0.5 kilonewton meter. Make sure that the units are consistent. If it is kilonewton meter, that means your bending moment also will be kilonewton meter. So point 0.5 into the a area in ABC, that will be minus half, and then base into height, that is the area of a triangle, plus half, uh, 10 into 2.5 minus half, 8 into 2, that will be the second negative area, and finally you'll find that this is equal to 1.75 kilonewton meter. And what does it mean? That means that the if you apply, if there's only a self weight in a beam, if you calculated the moment at D, you'll get a negative moment, which means that the 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 beam will be in a hogging manner at D due to its own self weight. So if we have to draw the beam, I'm just going to draw roughly. It's going to be, oh, it's going to be like this. Oh, sorry, it's going to be like this. Okay, so you'll see that this is sagging, and then this is hugging, and then this sagging. So you see that this will be hugging. So that's why you get negative moment. This is all correct because we follow the sign convention. So that's why it's very important to follow the sign convention. And then so that is moment. We already calculated the moment due to the uh, due to its own self weight. Now we are going to proceed with the equation part A. For the equation part A, it says that where would you place the live load of a 5 kilonewton in a beam to get a maximum positive. So looking at the um, influence line, the positive moment, the positive region in the influence line is between C to E. So we are going to place here the load C to E. I think I'll just write first. We're going to place all the self weight because it has its own self weight. Now we're going to place the live load of 5 kilonewton meter. So this is how we should place the live load to get a maximum positive moment at D. So now what is that value? Maximum positive at D due to live load will be equal to 5 into the area of the positive influence line. So the area of the positive influence line will be half into 10 into 2.5, and that will be equal to 62.5 kilonewton meter. So the maximum MD positive will be 62.5 kilonewton minus 1.75 kilonewton meter. Minus 1.75 is because that is the moment caused by its own self weight. So if we add them together, you'll get 60.75 kilonewton meter. So so this will give you the maximum positive moment at D when you place the live load in between C to E. And you can also solve this using your equilibrium equation and find the moment at D, and you will see that the moment at D will be exactly equal to 60.75. So this is why you can this is the benefits of applying the influence line, because with knowing the influence line we can tell where would we get the maximum positive moment at D. Okay, so that's how we apply the UDL for a maximum positive at D, maximum moment positive at D. And so for the part B, it says that we want to have besides the UDL of 5 kilonewton, where should I put my concentrated load? So we already know that this beam has its own self weight all over the length, and for maximum positive we know that we have to apply a UDL of 5 kilonewton only in the region C to E. And then on it says that for a point load, so for a point load we should apply for a maximum ordinate in the positive. So the maximum ordinate in the positive is at D. This is 2, but 2 is a negative, so we should not apply at F, we should not apply at B because these are negative ordinate. So the only positive ordinate is and the only positive maximum ordinate is at 2.5, and there's no other maximum positive ordinate in the beam. So which means that we're going to apply a point load exactly at point D, which is 15 kilonewton. So now your MD positive due to live load will be equal to, we already calculated here 62.5 from the previous part, and then will be plus 5 into 2.5, and that should give me 60, should give me 75 kilonewton meter. And so your maximum MD positive will be 75 minus 1.75 kilonewton meter. So this will be 73.25 kilonewton meter. So this is how you apply the influence line to get the maximum positive moment, due to life load 5 kilonewton meter, and the part B is, in addition to that, we add also the point load. So using influence, you can strategically uh, place the life load such that uh, you will see where to get the maximum positive moment. Um, that's it.